So the first problem we have for today is given the pole zero map that we have here on the right. This is P1, this is P2, this is P3, P4, P5, and it's clear that we don't have any zeros. And we want to answer these questions. The first question is, what is the system type? Can anyone tell me what is the system type of this system, given that the poles on this diagram? Any ideas? Okay, yes, it's a type 0 system. That's right, it's... And what is the system order? What's the order of the system? Correct. Yes, it's order 5 because we have we have 5 poles. Okay, from the diagram, which is the dominant pole pair? You recall what is the dominant pole pair, right? Dominant pole pair is the closest two poles to the imaginary axis. So according to this definition, which 2 poles do you think? Right, it's 1 and 2, these two. Very well. Now, if we say that the poles are given by this expression here, so we want to write down the transfer function of the best second order approximation, and we're assuming here that the system has a gain of 1. A gain of 1 meaning that that if we substitute with s equal to 0, we get, in the transfer function, we get 1, okay? So let me just... So now we have that our dominant poles are given by this expression, right? So, so it means that we have s, or one of the factors of the transfer function is s plus, or s minus p1, right? Times s minus p2, which when you multiply them together, you get s squared plus, let's see, this is minus p1 plus p2 times s plus p1 p2. So when you sum p1 and p2, you get minus 2, which gives us plus 2s. Then when you multiply them together, you get plus 3. Okay. So now that we have, so this should be the denominator of the transfer function, right? So g of s will be equal to, we have this in the denominator, s squared plus 2s plus 3. Now we need to find the numerator, right? And we recall that we said that we need the gain to be equal to 1, right? So what should the numerator be in order to have a gain of 1? Any ideas? If we put 1 here, um, what happens is that g of 0, right, will be equal to what? Be equal to 1 over 3, right? Which is not equal to 1. So that means that we cannot have a 1 here. Instead, we should put 3, right? So if we put 3, then g of 0 is equal to 3 divided by 3, which will be equal to 1. So we get that the gain is equal to 1, right? Another way to look at this is that we write the transfer function in the normalized form, okay? So this is the same as g of s is equal to, we take this element or the free term here and we divide by it, okay? If we divide by it, we get 1 plus 2 over 3s plus s squared, right? And similarly, we get, and this, we have here 3 times 3, right? We just factored out 3 from the denominator, and above we have also 1 times 3. So 3 cancels with 3, and we get this expression here. Again, if you substitute with s equal to 0, you will see that the gain of this transfer function will be also equal to 1.
Should there be a 1/3 in front of the s squared?
Yes, thank you. This is 1/3.
Okay.
All right. So now we want to ask whether the system is or underdamped, overdamped, or critically damped, right? And we can judge that from looking at zeta, right? So we want to compute zeta for this system. If we have the expression for the second order, we see that s squared plus 2 zeta omega n s plus omega n squared is equal to s squared plus 2s plus 3, which means that 2 zeta omega n is equal to 2, and omega n is equal to, omega n squared is equal to 3, right? So if we solve these two together, we get that omega n will be equal to square root of 3, and zeta will be equal to 1 over square root 3, which is definitely less than 1, right? So this means that this system is underdamped. If the system is underdamped, this means that the response of the system due to a step input will be thank you. The response of the system due to a step input will have will overshoot, right? It will have an oscillations that will overshoot or will initially overshoot the steady state. If it's critically damped, then Or if it's overdamped, then you don't get any overshoot. Okay. Next, we want to compute the time domain characteristics, like the settling time. So the settling time is 4 divided by zeta times omega n. And we found that zeta times omega n is equal to 1. So this is just going to be 4 seconds, right? Now the peak time is just pi divided by omega times square root of 1 minus zeta square. Can someone tell me uh, if we don't have omega n and 1 and zeta, but we only have the expression for the poles, right? We can read this off immediately from the poles. Can someone tell me what is this? Omega times square root 1 minus zeta square. So the poles of a second order system are given by this expression, right? So this is the same as this, right? It's the imaginary part of the expression for the poles, right? So if we have the poles, we can immediately read off from it the peak time and also the settling time, right? So in this case, we have that this in the expression we have is square root 2. So this is pi divided by square root 2, right? And this we found that this is 1. Now the final, or wait, the next one is the percent overshoot. The percent overshoot is equal to 100 times e to the power negative pi times zeta divided by 1 minus zeta squared. So again, if we only have the expression for the roots, right, of the second order system, and can we read off this expression immediately from the poles? Any ideas? What about if we multiply omega n above and omega n below? So this, you can see, is the ratio between the real part and the imaginary part of the poles, right? So again, we can read this off immediately. This is just going to be 100 e to the power negative pi times 1 divided by square root 2, which is going to be equal to, compute it quickly, negative pi over square root 2 which is approximately 10.8%. Any questions? And then the peak response is just 1 times the percent overshoot. So this is 1.108. Any questions so far? Okay, moving on. Just okay, so we want to find the permissible region for the poles of a second order system, okay, such that we satisfy the settling time less than 2 seconds, peak time less than pi over 2, and percent overshoot less than 5%. Okay. Now, like we said, the settling time is directly related to the real part of the poles of a second order system, right? So if we want TS to be less than or equal to 2, this means that we want 4 divided by zeta omega n to be less than or equal to 2, which implies that zeta omega n has to be bigger than or equal to 2, right? So we want the real part of the poles to be bigger than 2. This means that, or this will give us a line in the plane, right? A vertical line, such that the poles must lie to its left. Okay, so this we call, this is TS. This is the TS requirement, and we want poles to lie to the left of that. Next, the peak time, right? The peak time less than or equal to pi over 2 implies that pi divided by omega n square root of 1 minus zeta square has to be less than or equal to pi over 2, right? Which implies that omega n 1 minus zeta square, which is the real part, the imaginary part of the poles, has to be bigger than or equal to 2 as well, right? So this defines a horizontal line. Such that our poles must lie above this horizontal line. Right? And then finally, the percent overshoot to be less than 5%. Oh, percent overshoot to be less than 5%. This will constrain the ratio of the real to the imaginary part, so zeta omega n divided by omega n square root of 1 minus zeta square, right? We want this to be bigger than, yeah, actually less than or equal to so this is e, take the logarithm. So this will be the logarithm, the natural logarithm of 0.05 negative of that divided by pi. Right? Then this means that the ratio between these two has to be less than this quantity. So this defines two radial lines, something like this. And so we want our roots to lie above this one, above these two, right? This is the TP. And finally, we want, this is the requirement for PO. PO. So to satisfy all requirements simultaneously, we need to lie, or the poles need to lie in this green shaded region. Any questions? Okay. Now this problem is a little bit more involved, and so I need you to focus with me. This is problem 3 in homework. Um, Let me make sure that it's the correct homework. Um, hmm. Oh, so this is homework 3, not homework 2. This is the last problem in homework 3, and as you checked already, it's not marked red, so you don't have to turn it in, and that's why I'm going to solve it. So in this problem, we are given this block diagram. We have GC, which is a controller, and we have G, which is a transfer function given by this expression here. Okay, and we are told that this controller is given by this expression, and this whenever you see a controller of this form, it's called a PID controller. Or sorry, this is a PD controller, not a PID. This is a PD controller. And we want to find Kp and Kd such that we achieve a percent overshoot of less than 5% for the closed loop system and a settling time less than 2 seconds. So first we start with, so given that this is the expression for GC, right, and this is the expression for G, and this is a closed loop, we just simply compute the closed loop expression, right? So the closed loop, which is T of S, is equal to GC times G divided by 1 plus GC times G, right? So when you do that and you do that computation, you end up with that T is going to be equal to this expression here, okay? Now you can clearly see that the denominator of this expression is a third order polynomial. So we have not studied how to specify the percent overshoot and the settling time of a third order system, correct? So we only know how to deal with second order systems. In addition, we have this zero, right, which will also affect the properties that we know, right? Because our analysis is done for second order systems with no zeros. There is a way to deal with a third order like this, right? And Dr. Marco covered it at the end of lecture 6, which is basically treating the third pole as a perturbation and making sure that it lies far enough to the left such that it does not affect the performance, correct? However, as we can see, this is a bit complicated. So instead, or to do design for that problem or using that, because we don't know Kp and Kd here, right? So, and there, the expression for the roots of a third order polynomial is not very helpful either. So the best we can do, or in a situation like this, what we can do is that we try to design for the best second order approximation, okay? So first we look at the best second order approximation of this transfer function. The transfer function has 3 poles, right? Has a pole at s equal to 0, and a pole at s equal to -2, and a pole at s equal to -4. If I were to choose 2 poles out of these 3, so that we get the best second order approximation. Which are the two poles that I should pick for my second order approximation? Any ideas?
Shouldn't it be s equal to -2 because you want it closer to the uh, imaginary axis?
Right, so that's one. Now we want two, right? So what's the second pole?
0?
Yeah, exactly, right? So we will pick these two poles, s and s plus 2, or s equal to -2, because these are the closest two poles to the imaginary axis, and so we pick them to do our second order approximation. However, because we want also the system to have the same gain, or we want the second order approximation to have the same gain um, as the original system, right? We want to do this in the normalized uh, transfer function form. Okay, so to do that, first we write g of s, the system itself, in the normalized form by basically whenever you have s plus something, s plus 2, you just take the 2 or the free term as a common factor and bring it outside. Okay, so you get, for instance, in s plus 2, you get 1 plus 1 over 2 times s, right? And then you get a 2 um, outside. And similarly with s plus 4, you take the 4 as a common factor, and then you get 1 plus 1 over 4 times s. So, and then you do the simplification, you end up that the transfer function, or the normalized transfer function, will be 1 over 4, right, times s times 1 plus 2s times 1 plus 1 over s, 1 over 4 times s. So the dominant pole pair, as we said, is that p equal to 0, right, and p2 equal to -2, which means that we only need to focus on the first two factors in this expression here. Basically, we neglect this third factor here. This will give us the best second order approximation. Okay, and as we said, we neglect this one to say that the system is approximately equal to this one, and we call this our second order approximation as GA of S. Okay. Sorry. Then we try to close the loop around this expression, right? So we get T of A of S. This is the closed loop second order system, right? It's GC times GA divided by 1 plus GC times GA. And when you substitute with the expressions for GC and GA, we end up with, so I think there might be a computation error here. 1 second. Yeah, I think we're good. Yeah, so you end up with this expression here, right? It's 2 times s squared plus kd times 4s plus kp, right? And we still have this 0 in the numerator. Okay, so this will, depending on the values of kp and kd, this will distort the second order behavior of this system. So we need to take that into account as we do our design. If we do not take that into account, then we will see that there will be, like, if you pick Kp and Kd that satisfy the transient requirements for the second order system without the 0, when you look at the system with the 0, when you look at the system when you look at the characteristic for the system with the zero, you will see that it will not be satisfied. However, we can deal with this because, as we said, we just want this zero to lie far enough in the left such that it does not affect the behavior of the system, right? So we just simplify this transfer function into an expression that involves the left half plane zero, right, and the canonical second order system, or the form that we are used to for a second order system, right? Notice here that we multiplied above and below by k times p divided by 2, so that we get that the second order system will have a gain of 1. Okay, and we have this 0 just lying to the left. Any questions so far? Okay. So in order to continue, and in order to be able to neglect the effect of the 0, we need that, for instance, this is a second order system on this diagram, right? We have two poles at zeta times omega n, right? And then we have a 0 at negative a. In order to be able to neglect the effect of the 0 on the system response, we need that a divided by zeta times omega n has to be much bigger than 1, okay? For our system, if we try to compute the 0 here, right, a will be kp divided by kd, right? You can see here, if we just equate that um, kd times s plus kp equal to 0 will give us that s is equal to negative kp divided by kd, right? Which is, we say that this is equal to a. So a is given by kp divided by kd, right? And zeta times omega n is, so this expression here, right? This is 2 times zeta omega n, right? So zeta times omega n is just this expression divided by 2, right? So this is the expression here. It's kd divided by 4 plus 1. Now this requirement leads us to the fact that we want kp divided by kd, which is a, right, has to be much bigger than zeta times omega n, right? So let's say, for instance, we need that a divided by zeta times omega n has to be bigger than or equal to 10, right? Which is much larger than 1. So let me do this. Let me write it explicitly here, right? So this gives us an equation in terms of kp and kd that we need to satisfy, so that, or this gives us an equality, in fact, right? Gives us an equality in terms of kp and kd, such that such that the pole lies as the 0, my apologies, the left half plane 0 lies enough to the left such that its effect on the second order approximation is negligible. Any questions? Okay, let me continue then. So now we have, this is the first requirement that we have, right? We need that kp and kd, we need this inequality in terms of kp and kd to be satisfied. Now, the next inequality we have, now we want to satisfy the transient requirements, right? We have a second order system and we have expressions for zeta times omega n and for omega n as well. We want the settling time, which is equal to 4 divided by zeta times omega n. We want that to be less than 3.75 seconds. Okay, let me correct this here. Yeah, 3.7 5 seconds. Okay, which will give us that zeta times omega n, right? Which is, yeah, so this is correct. This will give us the zeta times omega n, which is equal to k d divided by 4 plus 1 has to be bigger than or equal to 4 divided by 4 divided by 3.75, which is going to be 16 divided by 15. Okay, so this is the second inequality that we need to satisfy in order so that we can satisfy the settling time requirement. Then the last requirement we have is that we require the percent overshoot, right, to be less than 5%, right? When we solve this inequality, you will see that you will get that zeta divided by, or approximately, of course, that zeta divided by 1 minus zeta squared has to be bigger than or equal to 3 over pi. We just square both sides to get this inequality. Then we manipulate it by multiplying, by multiplying both sides by the denominator, right? Assuming that zeta is less than 1, so that this expression is positive. Then we have then we solve basically for zeta square to get that zeta square. It has to be bigger than or equal to 9 divided by 9 plus pi square, which means that zeta has to be bigger than this, which is approximately going to be equal to 0.7. Now, we know what zeta is, right? Zeta is zeta divided by zeta times omega n divided by omega n. So zeta times omega n, we know the expression for it. It's kd divided by 4. And omega n, we can read it off from this expression here. This is omega n squared. So omega n is just the square root of that. So this is the square root of this is the square root of omega n squared. So it's a square root of kp divided by 2, right? This has to be bigger than or equal to 3 divided by square root 9 plus pi square. We just square both sides. Right. If we just, like if we multiply above and below by square root 2 times 4 and then just square both sides, we end up with this expression here. Any questions? So this is the third inequality that we need to satisfy. Okay, that kd plus 4 squared divided by 8kp squared plus bigger than or equal to 9 divided by 9 plus pi squared. Okay, note that so these are 3 inequalities in 2 unknowns, which means that they might be inconsistent, right? Meaning that we might not be able to find a solution for this system of inequalities. In such a case, if that case happens, we need to recall that this was not given as a requirement, right? This value, 10, we just made that choice, right? So if we're not able to solve it for 10, we can try to decrease this a little bit, make it 8 or 5, right? In that case, we know that the approximation will not be very good because the pole will lie closer to the, or because the 0 will lie closer to the poles of the second order system. However, luckily, if we try to solve this, these inequalities, we see that they are consistent, meaning that they give us a solution. And we typically solve these inequalities by basically graphing all the inequalities and looking at the intersection of them. Okay, in that case, I already did this for you, and I plotted the intersection of the three inequalities. In our case, the green shaded region is the intersection, okay, and we just pick one of the values inside this region, which is Kp equal to 4 and Kd equal to 0.35, okay. Notice that how the zero, right? So if we substitute with these values in the expression for the zero, we get that the zero will be approximately, will lie at approximately at negative 11.43, right? Which is quite far, right? It's far from the poles, right? Because if we substitute again with Kp and Kd using this value, we get that the Kp, or the real part of the poles will be negative 1.08 approximately, right? So we see that ratio between these two is definitely bigger than 1, which implies that the pole lies to like far enough to the left of the zero lies far enough to the left of the poles that we can essentially neglect its effect. So basically the second order approximation is valid, and we should expect that these values Kp and Kd will work for the second order approximation, right? For the best second order approximation. However, we need to be careful because we need to be careful about this, because the second order approximation is not the original system, right? So the original system will still deviate from this, because the original system has a third pole, right? Because it has a third order polynomial. There's a pole here that we totally neglected. So this pole could affect, and indeed will affect, the transient response of the system. So let's see how the transient response of this system looks like in a in MATLAB. Let me share my screen. Yes. Share. So as usual, we start with writing our S, right? And then expressing our transfer functions. G is G is the original system without the second order approximation. It's going to be equal to 2 divided by S times S plus 2 times S plus 4, right? And the controller is equal to Kp plus Kd times S, right? And we picked 4.5. Oh, yeah, I need to correct that in the notes. I will correct it. So we picked Kp equal to 4.5 and Kd to be equal to 0.3. This will give us, this completely defines our controller, okay? Then we look at the second order approximation, which we computed to be equal to 1 over 2 times S plus 2. Then we use the function feedback to compute the closed loop, the original closed loop system and the second order approximation as well. Then we compute the step response of both systems, right? So let's just say that this is step. So first we look at the step response using this the function step on the second order, the closed loop second order approximation. And we should expect that everything will work well because the zero is very far, right? So let's, one second. Yep. There we go. Let's zoom. So this is the step response of the second order system, right? If we try to look at the characteristics like the settling time and the peak response, we see that indeed the settling time is 3.89, which is not exactly at our requirement, right? Because we wanted this the settling time to be 3 point less than or equal to 3.75, right? However, it's not very far from that. Again, this is the effect of the zero because it's not negligible, right? It's very far, but it's not negligible. So in general, it will have an effect, right? And we see that the peak response or the overshoot is approximately 4%, which is luckily less than our requirement on the overshoot, right? We can try different values, like we can try to increase KP a little bit, right? So that, or maybe decrease this a little bit, KD, because as we know that, so let's see if this works. Well, not a lot of difference. Maybe if we make it 0.2. Oh, we should actually, yeah, we should actually increase it. Sorry, 0.35. 0.86. If we make it 0.4, we should get a better. So as you can see that as we increase KD, the settling time of the system is faster. However, if we look at, if we look at the original system, right, which is T, computed here with the same controller, but with the original transfer function, not the second order approximation, we will see we'll generally see a mismatch, right, between the two characteristics. For instance, we see that the original system satisfies or that the original system will generally have an overshoot that is larger than the second order approximation, and it'll also have a larger settling time, right? So we have a settling time of 4.24 seconds here, whereas and an overshoot of 13%, whereas the second order system will have a settling time of 3.82 and an overshoot of approximately 4%. So in general, we will have a difference between these two. However, as the pole and as the third pole goes even more to the left, and as the zero also goes to the left, we will see that these two will even go more into agreement, or the difference between them will be small. So I want to just show you one way to solve these whenever you have expressions like these. So this is Mathematica. Okay, it's a freely available tool for UCI students from Wolfram, and it has this function called region plot. Region plot takes in logical expressions and a range of values in terms of variables. In this case, we have KD and KP, and it basically computes the area in the plane that satisfies all logical conditions together. In this case, we have these three expressions. Let me first show you the plots of the regions so that you understand what I'm talking about. So we have three regions here. The region in blue, right? This corresponds to the first expression here, which is the expression on the settling time, right? Which was basically this, right? Then we have the expression or the value which is in yellow in the expression in the graph. This corresponds to the fact that we want the zero to lie far enough to the left such that its effect on the second order system is negligible. Then finally, we have KD and KP, or we have the requirement on the percent overshoot, which is the one in green, right? So we see that they all intersect in this region here. So if we put and here, and we see that they intersect in this region, and this region is the region of permissible values for Kp and Kd that satisfy all three inequalities simultaneously. If we see that if we have, so this, let me just put this in its original form. So this and that, let's multiply this by 10, right? This will give us the same expression we have. If we want a smaller value, for instance, we can make this 5, right? We see that the region or the permissible region will be larger, right? So if we try to decrease it, we see that the permissible region will be smaller. So we might not be able to achieve the required the requirements if this is large or if this is very large. Like for instance, if we put it to 20, we see that the region actually basically disappears, right? Because the three surfaces will no longer intersect. So let me show you quickly. You see that the three regions no longer intersect, which means that there's no solution that satisfies all inequalities simultaneously, right? Okay, this concludes my discussion today. I hope this was useful, and if you have any questions, you can come to my office hours on Friday. Thank you for your attention.
Thanks, Mahmoud. Take care.
You too. Bye.